So, any questions on what we're doing? Any questions? Nobody's looking at me? Okay. So what we're doing is giving you a bunch of tools that allow you to avoid doing epsilon and arguments. Okay. So we introduced the definition, right? But nobody likes to deal with the definition all the time because the definition is kind of unwieldy, hard to use. And so we build mathematically. We use the definition and we build these tools. We're not going to show you how we build those tools. That's done in a like a upper level math course, or sort of like a transitional math course, from the calculational math to the really theoretical math. So we're not going to show you the business of how we build those tools. We're just going to show you how we use them. Okay. And so the big one that we introduced last time was this one that we called I think something like limits and arithmetic. And it's basically showing you how limits and arithmetic interact. So it said something like this: that if you have two sequences and they converge to these numbers L and M, then the sum of the sequences is going to converge to the sum of the limits, right? The product of the sequences would converge to the product of the limits. The quotient of the sequences would converge to the quotient of the limits, as long as the second limit was non-zero. Yeah, then it said some other things. Okay, but basically, how do you combine these? How you can combine limits and arithmetic. Okay. So one way of thinking about this, just to make one remark, this could be thought of as a sort of like order can be switched theorem. Okay, that is, the first one, if you look at it, it says that the limit of a sub n plus b sub n as n goes to infinity is the limit of a sub n plus the limit of b sub n. Right? If we write it out, like the limit of the sum equals the sum of the limits. Okay. So what that's saying is that if you add the sequences together and then take the limit, or if you take the limits first and then add them, it doesn't matter. Okay, so you can add the sequences and then take the limit, or you can take the limits first and then add them together. Right? So limit and the plus sign can be switched. Right? Can commute. This is in mathematics we call this that the operations commute. Right? The order can be changed. Right? Like the commutative property in what you learn in elementary school. Okay, so order can be switched. And just to give you some sense of the power of this, what this says is something like this. So the limit of, we saw that the limit of 5 plus 1 over n was 5, right? It would be just as easy to see something like the limit of, say, 7 plus 1 over n squared equals 7. Okay, you could show those things. You could show those things using epsilon and arguments if you wanted. Okay, but what this theorem says is that you can do something like this. Then you can take 5 plus 1 over n divided by 7 plus 1 over n squared, and that's just going to be 5 over 7. Right, as n goes to infinity. If you take the quotient of those sequences, then the limit is going to be the quotient of the limits. Okay, and I challenge you to do this using the epsilon n argument. Right, it's not going to be that simple. Not going to be that simple. But this theorem says that you can do this. Okay. so this is kind of this is a really useful theorem. Okay, so that's where that's the second to last thing that we did last time. The very last thing was this thing called the squeeze theorem, sometimes called the pinching theorem. But I guess in this case it makes more sense to call it the squeeze theorem. It says that if you have three sequences, given sequences A sub n, B sub n, and C sub n, where A sub n is less than or equal to B sub n, is less than or equal to C sub n past some time for all n bigger than some capital N. If the lower guy, if the limit of the lower guy equals the limit of the upper guy, then the one in the middle will converge. The limit, the guy in the middle also has a limit. Okay, the guy in the middle also has a limit, and that limit is out. Okay, so we drew a picture of this last time. You know, you have some sequences. So there's some number L. Oh, hold on. I'm writing too fast as usual. So there's some number L, and you have these sequences, one sequence, and past some point, you don't really care what happens before that point. Okay, maybe you know there's no hierarchy between them, but past some point, you have this relation that A sub n is less than or equal to B sub n, less than or equal to C sub n. Okay, so you've got one lower guy, the A sub n's, you've got one upper guy. The C sub n's, the C sub n's, the A sub n's, and you've got somebody in the middle. Right? Somebody trapped between these guys. Okay, so that guy in the middle is kind of crazy. It bounces back and forth, maybe, but the upper guy and the lower guy ultimately converge to some number L. Okay, and so the one in the middle is going to have to converge to that number L also. So that's what the theorem says. If we wanted to, if this were an upper division course, we would use the epsilon n definition and show how this actually all works out. But I'm afraid we're not going to. Okay. If anybody wants to see it, I can show you sometime. Or I can point you to some video where I've done it in the previous course. Okay. Okay, but let's just do some examples. Okay, so here's an example. So last time we did an example using, I think, something like this, cosine of n over n, right? And we saw that that was bounded above by 1 over n and bounded below by negative 1 over n, right? And this guy goes to 0 as n goes to infinity. This guy goes to 0 as n goes to infinity. So just to remind people what we did last time, so the squeeze theorem says since this and this both go to 0, we see that this also converges to 0. Okay. So those of you who weren't here last time, I'm just going to give you a quick, I hope you watched it. You should have watched it. So Is that first example okay with everybody? We did it last time. Second example, 2 to the n over n factorial. Okay, the limit of 2 to the n over n factorial as n goes to infinity. Okay, does everybody know what n factorial means? Who can tell me what n factorial means? What does this n exclamation point mean? This is why mathematicians cannot be too emotional, right? Because we can't say the answer is 5, because yeah, that's completely different. Okay. Yes?
Isn't it like you multiply it by n minus 1 and then by n minus 2? And then
Yes, yes. So if I said the answer is 5, well, that actually means 5 times 4 times 3 times 2 times 1. Okay, so I can't say that. If the answer is actually 5, I have to say the answer is 5. Okay, because 5, this is 5 factorial, 5 times 4 times 3 times 2. Okay, okay. So we're looking at 2 to the n over n factorial. What do you think happens to this? What do you think happens to this? Can you even tell me what's going to happen to this number as n gets bigger and bigger?
The denominator is just going to get bigger and bigger.
Yeah, but the numerator is also going to get bigger and bigger, right? It's take 30 seconds and write down a few elements of this sequence. Just write down the first few guys, or write down a large one, or write down the 10th element. Okay, to introduce somebody and talk with them about what happens as what you think will happen as n goes to infinity. Okay, what's going to happen? Who can tell me, and who can sort of give a reason for what's going to happen? A1 is 2 over 1, right? A2 is 2 squared, 2 times 2 over 2 times 1. 3 is going to be 2 times 2 times 2 over 3 times 2 times 1, etc., etc. Right? What's going to happen as n gets bigger and bigger?
First one.
Hunter.
It's going to go to 0.
It's going to go to 0. Why?
Because in the numerator, as n goes to infinity, you're just multiplying by 2.
Yes.
But in the denominator, as n goes to infinity, you're multiplying by all the numbers below it.
Right, right.
So the denominator is going to be greater than the numerator.
Yeah, yeah. So basically you're noticing that with each step we multiply by something, but that something is smaller than 1. Right? And further, it starts to become much, much smaller than 1. Right? At the nth step, we're multiplying, or at the nth step, we've got 2 over n, 2 over n minus 1, 2 over n minus 2, down to 2 over 2, 2 over 1. Right? And so you see that we're multiplying by numbers that are tiny. Okay. Okay, so let's see how we would use the squeeze theorem to right? So you say, well, a sub n is 2 times 2 times 2 times 2 times 2 times 2. We've got 1, 2, 3, 4, blah, blah, blah. Okay, up to n. Okay, so here's one way of expressing this this observation of Hunter's using the squeeze theorem. You say, well, look, a sub n. I've got this number here, 8 over 6, right? The first three numbers give me this 8 over 6, right? And then after that, all these guys, this is less than a half, right? Less than or equal to half. The next guy is going to be less than or equal to half. All these things afterwards are less than or equal to half, right? Everything we multiply afterwards, less than or equal to half, right? So I've got 8 to the 6, so this thing, a sub n, is going to be less than or equal to 1/2 to the n minus 3 times this 8 over 6. Right? Right? Okay. So, and also, I know it's bigger than or equal to 0. Right? So this is going to be my squeeze, right? I've got the lower guy, I've got the upper guy. The lower guy goes to 0. The upper guy, as n goes to infinity, is 1/2 to the n minus 3. Also is going to go to 0. And so the guy in the middle has to go to 0. Plus e.
I'm not seeing where you found the n minus 3.
N minus 3 because how many terms are there? There are n terms total, and I've thrown out the first 3 terms, so I've got n minus 3 terms here, and each is smaller than 1/2. Okay. So then by the squeeze theorem, you say, well, this goes to 0. It is 0. Right? This thing also goes to 0 as n goes to infinity. Right? As n goes to infinity. So by the squeeze theorem, we know that a sub n, this a sub n also goes to 0. Okay. Okay, makes sense? Makes sense? Okay, great. Okay, a couple more examples. Maybe just one more, we'll see. Another example. So the limit of the square root of 4 plus 1 over n squared. Actually, let me make one remark before we do that. How do we know that the limit of, say, 1/2 to the n as n goes to infinity is 0? Okay. So it's sort of obvious, you could prove this, directly, with an epsilon n argument. Okay, it's sort of obvious, right? 1/2 to the n, right? As n gets bigger, this is gonna go to 0, right? And you could prove it using an epsilon n argument. Maybe you want to, if you're interested, you could try to do it as an exercise. Okay, but let me instead add on another tool that's useful. So let a sub n be a sequence, and f a function where f of n equals a of n, a sub n. as x goes to infinity equals L, then the limit of a sub n is L as n goes to infinity. Okay, as usual, when you put up a theorem, it's just sort of this formal statement. But there's a very simple idea. Okay, so here's the simple point of this theorem. What this theorem says is that if you have a sequence and you have a function, and this function happens to agree with the sequence whenever we're at a number, a natural number. Okay, so you have your sequence and you have your function, right? Then if the function converges as x goes to infinity, then the sequence converges as n goes to infinity. Okay, that's all that's saying. Okay, so basically we're saying that we can use some tools from calculus, because in calculus I hope you've seen limits of functions as x goes to infinity. Okay, and now we're saying, well, look, if we can find some function that agrees with this guy, then and the function converges, then the sequence also converges. Okay, so how do we know that 1 over n, as a 1/2 to the n converges? Well, you just say, so why does 1 over one-half to the n go to 0? You'd say, well, I know that 1/2 to the x as x goes to infinity is 0. Right, so you find the function, this function agrees with that sequence at the ends. Right? You know what 1/2 to the x, looks like this or something. Right? It's an exponential decay function. Right? So since that guy goes to 0, well, certainly the sequence 1/2 to the n goes to 0. Okay. Okay. Is that okay? Is that okay? Anna. Okay. So for example, no, actually, let me do an example of that afterwards. I'll come back to an example of this in a second, but for right now, let me do a second example of the squeeze theorem. So here it is, the limit of the square root of 4 plus 1 over n squared as n goes to infinity. Okay, so forget about this for right now. Go back. Let's think about the squeeze theorem. How one might use the squeeze theorem on this thing. Okay, so first off, what do you think is going to happen to this? What do you think the limit's going to be? Sorry? You think it's going to be 2. Why?
Because as it goes towards infinity, the 1
That's right. That's right. So you think, well, I'm pretty sure I know how this is going to work. Right? This 1 over n squared is going to become negligible, and this is going to be 2. Okay, and that's actually what's going to happen. So here's one way you could see this using the squeeze theorem. It's a little bit peculiar. I think most people wouldn't think to do this, but this is one way of doing it. You'd say, okay, I'm going to look at 2 plus 1 over n. Okay, and I'm also going to look at, how do I say this? Okay, so I'm going to say it like this. Here's the one I'm looking at. 4 plus 1 over n squared rooted, right? That is less than or equal to the square root of 4 plus 4 over n plus 1 over n quantity squared. Right? Right? Because I'm just making it bigger. Right? I threw in a 4 over n. Right? So it just became bigger. Okay. But maybe you recognize this thing, 4 plus 4 over n plus 1 over n squared. Does anybody see that we can make that a little simpler? The square root of this thing. I'll give 1 point on the exam to the person who sees it. Franco?
So it's actually just 2 plus 1 over n squared.
Yes, 2 plus 1 over n, 2 plus 1 over n, quantity squared, square root of it. Okay, so that's this 2 plus 1 over n. Maybe I shouldn't have written the 2 plus 1 over n up first. Okay. Okay. And on the left-hand side, I'm going to find something smaller. That's the square root of 4, aka 2. Okay, so then by the squeeze rule, by the squeeze theorem, this guy in the middle is going to converge to 2, right? Because the lower guy, I've got a lower sequence, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, right? Somewhere. And we've got this upper guy, 2 plus 1 over n, right? Which goes also to 2. And so the guy in the middle is trapped and also will have to converge to 2. So since this goes to 2, this goes to 2. This guy in the middle will also go to 2. Any questions? Any questions? Okay. Okay, so I hope you see how to use the squeeze theorem, right? Squeeze theorem. You basically have to look at your thing and make a guess as to what's going to happen, right? You think, okay, I think this is going to go to 2, and then you try to find something bigger that goes to 2 and something smaller that goes to 2. Okay. It's often not that obvious, but the ones in the book follow certain examples. So anyway, okay. Okay, so getting back to this thing about the limit of the function, if you have a sequence and you have a function that agrees with that sequence at the natural numbers, and if the function converges, then the sequence converges. That's actually pretty useful. So let's do a couple of examples. So here's one. The limit of n over n plus 1 as n goes to infinity is, oh, what is that? What's that going to be? Thank you. 1. 1. Okay. So now this one is pretty straightforward. So it's you don't have to worry about it. You could do as follows. say the limit of n over n plus 1 is n goes to infinity is the same thing as the limit of 1 over 1 plus 1 over n as n goes to infinity. Right? Because n over n plus 1 is the same thing as I could multiply by 1, right? This equals that, so this is that, right? As long as my n is not 0, and it's not, right? So I can multiply by 1 over n and say that these guys are equal, right? And then I would use my limits in arithmetic and say, look, the limit of the top guy is 1, the limit of the bottom guy is 1, so the limit of the quotient is going to be 1 over 1, right? So the limit of this guy is going to be 1 over 1, also called 1, by the limits in arithmetic. Right? Or if I had something like n over n squared plus 1, you see that you could divide again by n squared, say, right? And you get 1 over n on the top, you get 1 plus 1 over n squared on the bottom, right? And you see that the limit is going to be 0. Okay. So second example. Okay. So this example, pretty straightforward. You don't need any high-powered theorem to do it, but I'm going to use a high-powered theorem to do it anyway. Okay, so I'm going to say, well, look, the limit of this guy, I'm going to make my function. Well, my function is just going to be x over x plus 1. Right? My function is going to be x over x plus 1, and I want the limit of that as x goes to infinity. And I'm going to do something, crazy and say, I'm going to use L'Hopital's rule on it, right? I'll use L'Hopital's rule on it, and by L'Hopital's rule, that's going to be the limit of 1 over 1 as x goes to infinity. That's 1. So by L'Hopital's rule. Close your eyes for a second. So anybody raise a finger if you don't know what L'Hopital's rule is? Okay. Put down your fingers. So there are a few people that don't know. Let me quickly tell you what it is. It is a cool application of the mean value theorem that says the following. For us, it's like this. The limit, if the limit of f of x as x goes to infinity, and the limit of g of x as x goes to infinity are both 0 or both plus or minus infinity, then the limit of f of x over g of x turns out to be the limit of f prime x over g prime x. So the thing that we were just looking at, you see that the top goes to infinity and the bottom goes to infinity, right? And so you'd say, is the answer infinity over infinity? No, it's not. By L'Hopital's rule, this limit is going to be the same as the limit of the quotient of the derivatives. So you take the derivative of the top, you take the derivative of the bottom, and you say, oh, by L'Hopital's rule, this is going to be 1. like using a bomb on, it's using something very powerful on something really weak. We didn't need to do that. Okay, but we did it just to show you that one could use L'Hopital's rule. Okay, let me give another example. The limit of natural log of n over n as n goes to infinity. Okay, so we do the same thing. We say, let's create a function. Let f of x be natural log of x over x. And we want to look at this. Right? Well, again, this is infinity over infinity. Right? This is infinity over infinity, so we apply L'Hopital's rule, which in some book I saw a long time ago, they put like an H in a circle. So I have this habit of putting an H in a circle whenever I use L'Hopital's rule. So you say, okay, well that's going to be the derivative of the top divided by the derivative of the bottom. Right? And so you end up with 0. Okay, so I hope people are getting some sense of how to do this. What if I have, say, the limit of e to the n over n to the 10th power as n goes to infinity? Take 1 minute and try to do it doing exactly the same thing that we're doing now. Okay, turn to somebody nearby and talk with them, please. Okay, so what's going to be your function? What's your function going to be? Well, of course, it's going to be e to the x over x to the 10th, right? And as you let x go to infinity, both top and bottom are going to go to infinity, right? So you start differentiating, right? You say, okay, by L'Hopital's rule, that's going to be the limit of e to the x over 10x to the 9th as x goes to infinity, right? But both top and bottom go to infinity, so you say, well, by L'Hopital's rule, that's going to be the limit of e to the x over 10 times 9 times x to the 8th as x goes to infinity, right? But both top and bottom go to infinity, so you use L'Hopital's rule, and you keep on going, right? I'm not going to do it again. you end up with 10 factorial on the bottom. Right? Okay, so that's infinity, right? That's infinity. Right? And so this thing turns out to be infinite. So it diverges. Yeah.
Can you explain why you use L'Hospital like multiple times?
Well, because L'Hopital's rule tells you a trick you can play when both top and bottom go to infinity. So this e to the x goes infinity, e to x to the 10th goes to infinity. So you say, I've got infinity over infinity, I'm going to use L'Hopital's rule. But then you end up with this, e to the x over 10x to the 9th, as x goes to infinity. That's still infinity over infinity. So I'm going to use L'Hopital's rule again. Okay. So if I see infinity or infinity, one of my first tricks to play is, maybe my only trick to play is L'Hopital's rule. So, and you keep on doing it, but at some point it turns out to be e to the x over 10 factorial. Well, that's infinity over a finite number. Well, that's just infinity. Okay, so this can be used to get the following results, that the limit of n to the 1 over n is 1. So there are a couple of things that turn out to happen, but maybe I'll talk about them in more detail at the beginning next time. Okay. Instead, let me introduce one more useful tool. Okay, and it's this. Okay, so remember we had this sequence, the limit of square root of 4 plus 1 over n quantity squared, right? We had this limit. Okay. Now, what would have been nice would be the following power. Like, if we could just say, this is just going to be the square root of the limit. Right, the square root of the limit. If we could pass the limit through the square root function, right? Then we'd say, okay, the limit of the square root is the square root of the limit. And so, and I know what this limit is, right? This is the limit, this is 4 plus 1 over n squared. Well, that's just going to be the square root of 4, right? So that would be desirable, right? If we could commute the function and the limit, then that would be good. Okay, in fact, we can. Okay, so here's the theorem. It says, if you have a sequence and you have f a function, if the sequence converges to L and the function is continuous at L, okay, if the function is continuous at L, then the limit of the function of the sequence equals the function of the limit of the sequence. That is, you can change the order of the limit of the function. Okay, so let me give you an example. If I say the limit of cosine of pi over n as n goes to infinity, you would say would say, well, I know that this cosine function, I know that the limit of pi over n as n goes to infinity is 0. Right? And I know that cosine is continuous at 0. So that allows me to change the order. Right? So I can change the order. So this is going to be equal to the cosine of the limit, in other words, the cosine of 0. Okay. If I'm talking about the limit of the natural log of n over n plus 1, well, what's this going to be? So maybe take 10 seconds, look at it, make up an answer in your head. What is it? 0, right? This is going to be the natural log of the limit, which is the natural log of 1, namely 0. Right? And you can do this because natural log is continuous at 1. E to the 1 over n as n goes to infinity is going to be what? Somebody just tell me? It'll be 1, right? Because you can pass the limit through the exponential function, right? And get e to the 0, which is 1. If a sub n converges to L, then the limit of the absolute value of the a sub n's is going to be what? Elizabeth? You're not sure?
Is it just L?
It's not L. The absolute value of L? Yeah, the absolute value of L. Right? The absolute, in this case, the absolute value is your function. Right? The absolute value is a continuous function, right? It's not differentiable, but it's continuous. Right? So you know that the limit of the absolute value is going to be the absolute value of the limits. Well, that's the absolute value of L. So this is a very, very handy theorem, right? And you can iterate it, right? If I said the limit of the cosine of e to the pi over n, like this, right? You don't have to worry, right? You just say, well, that's going to be the e to the 0, that's 1. The absolute value of the cosine is 1. Right? You can use multiple instances of it. Okay, that's it for today. So let me hand that to homework if you have time to sit around.